Okay, we're going to talk about alloy steels. This is lecture number 4. And again, alloy steel means it's a steel that has alloys besides just the carbon in it. So let's begin. So some of the things you might want to improve by adding alloys, and by the way, these alloys are relatively expensive. So these steels are not cheap, and they're in there typically to provide some sort of improvement in certain aspects. If we want to, let's say, increase our ability to harden something, number one here, we might put chromium or molybdenum or something like that in there. So we're going to talk about what different types of alloys we would add and why we would add them. So hardenability, machinability, strength through heat treatment, strength as manufactured, corrosion resistance, and retention of hardness and strength at high temperatures. So we'll go through all these and tell you why you might use these things. Generally 3 classes of alloys, and it has to do with how much of the alloying materials in that steel. Also, the cost of that alloy or that steel will be greatly affected by how much of these alloying elements is in there. Okay, so constructional, gears, levers, things like that, up to 6% alloy content. Things that have to be strong, but not necessarily hard. Okay, they might be somewhat hard because strength comes with hardness to some extent. But alloy tool steels, these might be things like drill bits or dies or something like that, where we're going to have to have some sort of resistance to something. It could be resistance to wear. It could be resistance to temperature. All different kinds of steels there. You might want something that holds a really good cutting edge, like if you're making a knife for something. And then we have special alloy steels that were designed exactly for specific purposes. Okay, so let's next slide. So we're going to go through each alloying element, and these are just kind of generic. Why would we add these things? But one of the things that we use chromium for is ball bearings, okay? But the most important thing probably is that it is the active ingredient in stainless steel, okay? If we don't have a minimum of something like 11% chromium, stainless steel is not stainless. So most stainless steels might have 11, 12%, but the really good ones have about 18% chromium, and they can go higher than that. The reason why chromium works is that chromium, it's kind of a weird thing that chromium is actually not corrosion resistant, so that it makes the steel corrosion resistant. And what I mean by that is we have some stainless steel right here, okay? If I scratch this with another piece of metal or something like that, what I would do is I would scratch the oxide of chromium off the surface, and then immediately it will form again because chromium really, really likes oxygen. And so the first thing it does is it forms chrome oxide very quickly, okay? And the cool thing about that is chrome oxide is impervious to more air or oxygen getting at the steel beneath it. So the chromium then is protecting the steel by not being corrosion resistant to some extent, and that it's oxidizing, creating a layer of oxygen resistance for the rest of the steel. So there's other materials that do that as well. Aluminum does it to some extent, things like they actually made a carbon steel. They put copper in it. It's called Core 10 steel. So if you drive by, a lot of times you drive by like a railroad crossing, and there's a little house there. Sometimes they're aluminum, sometimes they're like rusty color, and you're like, oh, they should paint that. It's actually probably made out of Core 10 steel, which means that it rusts. But then once it gets a initial rust layer on there, oxidized layer, it doesn't rust anymore because that particular oxide of iron is impervious to more oxygen getting at it. So kind of funny that the reason why something is corrosion resistant is that it's not corrosion resistant. Okay, so cobalt. Cobalt is usually added for high temperature strength. So so it can be added from 5 to 12%. Usually it's used in steel drill bits and things like that where we want to have resistance to higher temperatures. It doesn't really affect the hardness so much as it does the strength at high temperatures. Manganese is for wear resistance, and so there's special manganese steels that are for crushers, rock crushers, things like that, where you have impact resistance, and they're really hammer mills are really good at this. So if you go to a junkyard, they have these things called, it's a hammer mill. It's basically a big drum, and it's got a bunch of hammers that are attached on little pivots. And the hammers are, I don't know, sometimes they're 300 pounds. It's got a big blob at the end, and it looks like a hammer. And they flail around very quickly. I don't know what there's in Miller Compressing in Milwaukee, it has a 6,000 horsepower motor that drives one of these things. It's the largest motor in Wisconsin. And so you put like a car into that, and it basically just kind of hammers it, and then the chunks of it get stuck inside of this cage, and the hammers are bouncing around inside the cage, and essentially there's little holes about this big in the sides of the cage, also made out of manganese steel, and it can't get out until it's that size. So they'll literally put a car in there, and in about 15 seconds, the complete car is in pieces this big or smaller. That's including the seats, the engine block, the crankshaft, all that stuff breaks down into chunks, plastic, everything. And then they have special equipment that sorts it out. So it's pretty cool. Okay, so some other alloying elements, molybdenum. Most people can't say this. If you can't say it, just say moly. Okay, molybdenum, it has a B and a D next to each other. So moly, high strength and toughness. They usually use it in really fine wire if you're trying to draw wire. But you may have heard of chrome moly steel. It's kind of it's a word that's thrown around a lot. It's used for like bike frames and airplane frames. It's if you do any car racing, the roll cage and everything, and the frame itself is probably made out of this chrome molybdenum steel. And it's usually like a low carbon steel, low or medium carbon steel. It has very good strength. You can weld it, and chrome molybdenum steel is used for high strength applications. Nickel is added usually for toughness. Armor, also stainless steel. It's a secondary ingredient in stainless steel. What it does is nickel will make stainless steel non-magnetic. And there's a lot of stuff that I would have to explain for you to understand why that is. But essentially, the type of stainless that is non-magnetic, like this is probably non-magnetic stainless, is the good stuff. So if you're going to buy a gas grill or something like that, what you want is all the stuff in and around the flames, especially the burners themselves, to be made out of non-magnetic steel. So if you go to the I don't know, wherever they're selling grills, Home Depot or whatever, take a magnet with you and start touching things on it. The casing that around the outside doesn't matter as much as the inside. If you ever own a grill, you'll find out that the stuff near the high temperature is what oxidizes very quickly. As you increase the temperature of a metal, it oxidizes much faster. So you want everything around it and the actual burners themselves to be non-magnetic stainless steel. You didn't know it, but there are different kinds of stainless steel. Some of them are magnetic, some of them aren't. So we also use it for armor plate. It's expensive stuff, so We should only put it in there if we need to. Okay, so tungsten. Why do we use tungsten? Very high melting temperature, high temperature hardness, very stiff. If you have tungsten by itself, is very stiff. They actually make a tungsten alloy for some machine tools because you want something to be you can't have it deflecting when the tool's cutting something. If it starts to deflect, it'll start vibrating, and then that actually will create a bumpy surface on your lathe part or whatever it is. Okay, so they make some tooling out of that has a very high stiffness. Remember the elastic modulus we talked about like in the first lecture? So elastic modulus, remember, is the slope of the stress strain diagram, and therefore I think the stiffness of or the elastic modulus of tungsten is something like 50 million psi, where steel is only 30 million psi, aluminum would be 10 million psi. So that's just a kind of interesting thing about it. It also melts at 6,000 degrees, so in order to get that to go into solution, when we put tungsten into the molten metal, it has to dissolve. It can't really melt, actually, because we don't have anything that can get to 6,000 degrees very easily. The arc furnace gets, kind of those temperatures near the surface. So when we are alloying, if you do it in an arc furnace, and vanadium, same thing. It's at a very high melting temperature. So tungsten and vanadium are sometimes added to some alloys. These are usually added for like drilling or something like that. Machine tools. Okay. Vanadium is also in very small amounts in the old-fashioned Damascus steel, the real Damascus steel, which is something that I mess around with in the lab occasionally. Okay, so what is high-speed steel? You may have seen, if you buy a drill bit and you look on the side of the drill bit, if it's big enough, some of the small ones you can't read it, but if you look on the side of it, or if you look on the package, it might say HSS, or high-speed steel. And what that is, it's a group of alloys that are resistant to high temperature deformation. In other words, we're drilling something and that you want that edge to stay hard, but remember that when you're drilling something, it builds up heat right where you're shearing that material off. And so a couple things can happen. You can snap the thing if you put too much force on it, okay, because it's fairly brittle. You could heat it up too hot where it's going to actually soften and then kind of smear and deform, and sometimes it welds right to your workpiece. Or it's going to cut the thing really nicely and stay pretty much in one piece. Okay, it'll eventually wear out, but if you just heat it to certain temperatures, a high-speed steel will go to much higher temperatures than most steels. So what are we gonna add to it? If you look at the carbon content, it's between 0.7 and 1.5% carbon. So we know that this is a high carbon steel. Okay, it contains chrome, vanadium, molybdenum, tungsten, and cobalt. Okay, sometimes, most of these alloys, they combine with carbon to make hard particles, so that are really wear resistant. Okay, the cobalt just gives it overall higher temperature resistance. So you can machine things right at the cutting edge up to 1100 degrees Fahrenheit, whereas a normal steel, if you get that above 450 Fahrenheit, it's going to start to soften on you. So it's also known as losing your temper, and that obviously is an expression, and it comes from when you're doing something like drilling, or let's say you're sharpening a chisel and you get it a little bit too hot and it turns blue. So that means you lose your temper, which would probably make you pretty mad, because the whole process of hardening it and then tempering it, then it has to be done over again. So here's where we come to okay, well, if I want to buy some steel, what do I buy? Okay, and how do I explain to someone what it is I'm looking for? Now, the most popular steel pretty much ever is 1018. So you see this one, it says AISI 1085. If you put the number 18 at these last two digits, that's 1018 steel. It's about 0.18% carbon, and it is what I call the idiot-proof steel I mentioned before. Okay, so 10 stands, the first two digits, 10 stands for plain carbon. And then if the number changes, like 41 would be chrome and molybdenum or chrome moly steel. Okay. One thing I do want you to know, there's like an 11 and a 12. What those are is they actually add sulfur back to it and some manganese. And if you have sulfur and manganese, they make little particles which help for machining. So let's imagine if you've ever machined something, the chips are coming off. You're scooping off metal from this piece, right? Somehow you're machining material away, and in scooping that material off, it creates a chip, basically a thin sliver of metal that comes up. If we add manganese and sulfur, it makes little particles that are kind of distributed all throughout the steel. And what happens is when that little chip is bending up, it tends to break off. Well, why is that good? Well, because it doesn't snake all around inside the machine and tangle everything up. Otherwise, you basically make a piece of steel wire, kind of flat looking wire, that gets wrapped in everything. Okay? So if you want your steel to be more machinable, what you do is you can add sulfur, you can add phosphorus, and you can add lead, actually. So sulfur, phosphorus, and lead are considered elements that make it a free machining steel. Okay, so understand what that is. And then 51, 50, it's 52 100 or 51 and 52 are chromium. That would be a ball bearing steel. So this one's got 1.5 or 1% chromium in that steel. Okay. So that was the first two digits. And by the way, where do you find that information? You look that up in a catalog. If you're going to buy some steel, you can look it up online to see what's available. Okay, it's kind of the iterative problem. You find out what people are using for something, then you look at the properties. You think, okay, well, is that good for the thing that I'm trying to make? Okay, and then you not only have to figure out what the material you want to use is, the manufacturing process is kind of like hand in hand with that, but also if you want to heat treat it, which you usually do, okay? If you're trying to make something really strong or, hard or whatever, you have some application. Okay, so the numbering system, the two last digits, is the carbon content, and it's kind of weird. We move the decimal point from the back here 2 places to the left. So this is 0.85% carbon. So what kind of carbon steel would that be? A low, medium, or high? Okay, it's a high carbon steel. So 0.85 would be a high carbon steel. Again, that you might see again sometime in the near future. Okay, so that's the numbering system for steel generally. By the way, AISI or SAE, sometimes they have here, means the American Iron and Steel Institute or Society for Automotive Engineers, and they both help make standards for materials back in the old days. Okay, so let's say I want a specific steel that's going to do something like be able to withstand sudden impacts. So I might make an S type steel. Now, S type steel has like S1, S2, S3. So you'd see this letter and a number, okay? So A2 is a real popular one. And I'm going to tell you right now that what you're doing for your screwdriver, that little rod that you're using, that is a O1 oil hardening tool steel. I'm going to show you something real quick here on how to actually look some of these things up on the internet. Okay, so I've looked up MatWeb. Now, MatWeb is a material property database. And so I got to kind of know a little bit, though, about what I'm looking for. So it's just matweb.com that I looked up. Okay, then I go over here to this little search thing here. And what I'm going to do is I'm going to put in here an alloy. Let's say I put in, so O1 tool steel. Now, if I just put O1, it'll probably come up. Let's see what we find here. Okay, so AISI type O1 oil hardening tool steel, oil quenched at 800 degrees C and tempered at 425. Okay, so this is, you got to kind of know what you're going to do to it, but I could use this crucible steel has an alloy, Latrobe. Sometimes people actually, it's kind of like, it's the internet, so there's some stuff that's on here because people are trying to sell things. Let's look at crucible steel. I like crucible steel. So let's see what they say. Here are their, so it says it's an oil hardening tool steel, may be hardened from fairly low temperatures with little size change. This grade combines deep hardening qualities with fine grained structure, affording good initial production runs and good continued production after grinding. That wasn't very useful. Okay, Rockwell hardness. Now this one here, it says hardened then tempered. It doesn't say what temperature. Oh yeah, here we go. Tempering temperature. So if we tempered at, and this is 1,000 degrees Fahrenheit, they do have the English units here, it's 39 to 41. Now, is that a high number? Now remember that a soft steel might be Rockwell 10 to 25 or something like that. So this is much harder than that. The hardest you can get is like 65. Okay, so this untempered is from 63 to 65 Rockwell C hardness. If we temper it at 1,000 degrees, it's 39 to 41. If we temper it at 300 degrees, it's 63 to 65. So the deal is, the higher the temperature we temper it at, so we heat it up, we quench it in oil, which is what you're doing, and then if we put it in at 600 degrees, or 700 degrees is what we're doing actually, in our screwdriver, right? So this is the alloy we're using for a screwdriver. You're putting in the furnace, you're quenching it, and then it's probably 63 to 65 hardness when you quenched it, very brittle. And then we temper it at 700 degrees for an hour. And so it'll be probably around 52 Rockwell C hardness. Okay, so we come down here, and here's some other things we might want to know. Impact values. Well, this is really pretty important. If we tempered it at, well, let's see, at 600 degrees, it has 32 foot-pounds. And we temper it at 300 degrees, it has 14. So you can see that this impact strength. In other words, when there's a sudden impact, what'll happen is it'll either fracture or it'll bend, it'll deform, okay? Or it might spring and go back to its original shape, okay? So we want it to spring and go back to its original shape. So if we have a screwdriver and I got it in a screw and I'm turning as hard as I can, you don't want it to snap off, you don't want it to bend, you want it to just, if anything, it just twists like a spring a little bit, and then, turns the screw, and then it goes back to its original dimensions, okay? So let's look back here. Now they don't have 700 degrees, but you can see that if we did have 700, it would be something like 34 foot-pounds. So it's really going to absorb a whole bunch of energy, okay? So that's good, unless it bends, okay? Here's what's in it. 0.9% carbon, 0.5% chromium, most of it's iron, and then a little bit of manganese, small amounts of tungsten and silicon, okay? So essentially the active ingredients are the carbon, the chromium, a little bit the manganese, and the tungsten, okay? The silicon's in there for a different reason. So that's interesting. Is this a low, medium, or high carbon steel? Well, it's 0.9%, so it's a high carbon steel, okay? Let's look at one of the other ones. What else was on there? Let's look at W1. W1. Now, some of these have a big range of, let me see, water hardening tool steel. W1. Let's see what that is. And this one's tempered at 350 degrees or 660 degrees Fahrenheit. Water quenched from 1425. So now this one's a little bit better because it gives you mechanical properties. This one's really strong. The tensile strength is 244,000 pounds per square inch. Remember we were just talking about your electrodes for welding. What are they supposed to be? A minimum of 60,000 pounds per square inch. This is 200,000 pounds per square inch, so it's really strong stuff. Okay. The yield strength's 218, and it only has 3.5% elongation in this particular state. It is Rockwell 50 to 51, so it's not super hard because it's been tempered back. It's 600 degree temper. So if we were going to make a knife out of this, we wanted this to be harder. What we would do is we would quench it and then temper it at a lower temperature, like 300 degrees or something like that. Okay, so the carbon content, this is crazy, 0.7 to 1.5. It's got a huge range in there. Usually it's right around 1%. So what else does it have in it? It's got a teeny bit of molybdenum in it. And everything else is less than, which means it's not in there for any particular reason. So it's got manganese. Wait a minute, did I look at that wrong? Yeah, manganese and silicon. So I misread that, I think. So this is manganese and silicon are the main ingredients. So really, there's nothing added to this. This is just plain carbon steel with a high carbon content. Okay, so if you ever watched Forged in Fire, a lot of times they'll use 1080 steel. So W1 kind of is, it gives you a big wide range. It would probably, 1080 would fall within that range. Or you can actually specifically say, I want 1080 steel and get it. And there's 1084 and there's a couple other ones. But they're all plain carbon steel, and they're pretty forgiving when you forge with them. But sometimes they're hard to get it completely hardened because you have to quench it in water. Or really fast oil. If you watch Forged on Fire, there's this big flame when they quench things. It's because they're using a fast oil, and it doesn't always get completely hard. And the idea is that they're trying to completely harden the thing without warping it. Okay? So that's it for MatWeb. It's a very good tool, and those mechanical properties and physical properties and chemical compositions are really important for making your decision on what you're going to use. Okay, so you can see that with using MatWeb is you can determine what's in things, what things are used for. So it'd be a really good tool for trying to determine mechanical properties and to see if the material you chose is the right material for the job. Okay, so this is pretty much the last slide. So let's go over. So oil hardening means that I harden this in oil. If I harden oil hardening tool steel in water, it will crack. Okay, water hardening has to be hardened in water. If you try to harden or W1 in oil, it doesn't get very hard. Okay, so as we go from water to oil to air, the cost might be a ratio. If this is a 1, this might be a 4, and this would be an 8. So this is probably 8 times more expensive than the water hardening steel. Water hardening steel is just plain carbon steel, maybe 1%, maybe a little bit more. Okay? Oil hardening steel is got some alloying elements like we looked up, and then air hardening steel has yet more alloying elements like we looked up. Okay, and then there's other ones. H13 is used for die casting dies. So Mercury Marine, they make huge dies out of H13. It's really expensive. It's actually not very hard, and what happens when you make a big die out of a hardened steel, or really strong steel, and you heat it and cool it and heat it and cool it. In fact, you're only heating it on the surface of it, whereas the rest of it is just absorbing that heat. So you have hot here, and then it cools down because you got cooling water behind it. So hot, cold, hot, cold. We're making propellers, we're making engine blocks or whatever. And the molten metal comes up against that surface under high pressure. It solidifies, the die opens up, the part pops out, kind of like injection molding. Okay. Over time, the metal gets hot and cold, and then eventually cracks. So over, like, let's say 100,000, maybe 200,000 cycles, eventually you start getting little cracks. And you may have seen these before. If you work with old lawn mowers and stuff like that, the engine block is all die cast, okay? And so sometimes when you look at these things, they look like they're crazed, like they're cracked. And what that is the die is starting to wear out, and the metal is starting to get down in those little cracks and create a kind of a crazed surface. And what they'll eventually have to do is replace that section of the die. So, but the deal is that the H13 steel lasts a lot longer than a normal steel would. Okay, that's all I have for the different types of steel now, and we'll see you next time.